Um, I've said this to you guys before. I'm going to say it a lot over the next, especially month. My goal as a teacher is not necessarily to teach you chemistry or math. I mean, I'm going to teach you those things, but I want to teach you what I consider to be some of the more important skills, like organization, keeping track of your marks, honesty. Right? I think those are more important. Here's another one. When it comes to taking notes, I don't see a lot of value in writing down every single thing. Because if you guys look through the notes we're going to do today, there's a lot to write. Like, you'd be writing for quite a long time. But it probably makes a lot more sense to change the way that you learn rather than write down these notes here. The advice I'd give you is grab a highlighter. Like, if you want a highlighter, I can probably get you one. Or write down the stuff that we talk about. Okay? I think this is a bit of a higher level of being able to learn. Is rather than spending all your time scribbling down as fast as you can, be engaged in the conversation. Okay, and that's one of the things that I like to expect out of my students is that when we're having a conversation like this, please don't be having your own little chat on the side. Engage in our discussion. Okay, this isn't notes. This is discussion time. Does that make sense? And I find that helps kids learn a whole lot more. Being able to do that rather than frantically writing down. If you don't have a copy of these notes, don't stress it. They're online. Right? If you don't know where to find them, I'll show you later. Fair enough? Okay. So today my goal is I want to chat with you guys a little bit about thousands of years of chemistry history and how slowly but surely scientists have redeveloped their knowledge of matter. Okay. Let's start with just the basic definition of matter. I'm just going to write this off to the side. This would be a good thing to kind of add maybe. Do you guys know what matter is? Have we given the definition of it before? Go ahead.
Anything that takes up space and has that.
That's actually the two parts to it. Yeah, it has to take up space, and it has to have a mass. Okay, let me give you some examples of matter. This is matter, because in 3 dimensions, there's space to it, and it weighs something. You know what? We actually did this in our lab. This is really density, because isn't mass and space being like volume, weren't they the 2 components of density? Right? No. If it has a density, if you can weigh it, and if it takes up a certain amount of space, then it's matter. Let me give you some examples of things that aren't matter. Fire. Right? Fire itself, well, give me a sec on that one. Fire itself actually takes up space, right? Clearly the flames were, yay high, right? We can measure that. But does the fire actually have a mass to it? Not in that way, because it's actually energy. Energy doesn't actually weigh anything. So that would, like, fire is not considered matter. Makes sense. Not that I expect you guys to get to this point here, but maybe you've ever heard of something called a singularity. So maybe you see those in like Star Trek movies or something like that. They're what's believed to be at the center of black holes. A singularity is considered to be infinitely heavy, but literally take up no space at all. And so that would be the opposite, where it actually can be weighed. We think we know how heavy it is, but it's actually so infinitesimally small that it actually takes up no volume. And that's what sometimes people believe to be its black holes. Anyone ever heard of a vacuum before? Not like the vacuum cleaner, but like a scientific vacuum. What's a vacuum in science? Yeah, space with nothing in it. Imagine that you had like a jar, and it looked empty, right? Well, it's not actually empty, because what's inside the jar? Air. What if you could literally suck all of the air out of the jar? Now, sometimes we do this. Like, I have a vacuum sealer at home that I use to seal like frozen meat in my freezer. Anyone ever seen one of those before, where you like suck all the air out and it like squishes in? Well, if you were to able basically to suck all of the air out of a container, and the container was strong enough that it wouldn't like collapse in on itself, then that would be a vacuum where there's space, but there's nothing in that space. Actually, outer space is a vacuum, right? If you were to go into like past the moon and into like astronaut type stuff, right? If you were to, well, that's why they have to wear spacesuits, right? Because if they took their spacesuit helmet off, there literally is no atmosphere. There's no oxygen there. There is literally nothing there. There's a nitrogen molecule right there. There's an oxygen one here. There's an argon one right here. And I can breathe all those in and survive on Earth, right? But if I were to go to outer space, we don't have those, right? That's a vacuum. So those would be examples of things that aren't matter. Right? But pretty much everything else is matter if it takes up mass and has space. my goal today is to walk you guys through then the history of how humans have learned about what stuff is. Because really, matter is just the stuff we see around us. Does that make sense? So let me talk about some history from like thousands and thousands of years ago, like 3000 BC. You guys know what the BC refers to? Yeah, so we're talking like 3,000 years before Christ. It's now the year 2017, so we're talking like 5,000 years ago. Okay. There were scientists. They didn't wear lab coats and glasses like you guys did, but they were working on things like how to use metals to do cool stuff. Like, here's some examples. They would use gold for jewelry, right? Gold has always been a very, very valuable substance, right? And so ancient scientists would be trying to refine gold and make it into rings or into statues or whatever it is they made it out of, right? Or they would have used copper, right? And what would they use copper for? Tools and weapons. I mean, again, think 5,000 years ago. We're not talking sophisticated societies. We're talking people who literally needed to hunt with a spear. Well, if you're hunting with a stick, or if you're hunting with a stick with like a pointy thing on the end to actually kill the wildebeest you're trying to get to. You get what I'm saying here, right? Like being able to refine and mold and melt and work with copper, that was valuable, right? Not only just for weapons, for like trying to kill, like, hunt for animals, but tools. Like say you were a farmer and you wanted to work with the land, you need to somehow till the soil and mix it up, right? Nowadays we have tractors for that and different machines, right? Well, back then they would have had to use like a hoe. You know what I'm saying here? And so if you had a blade, that works way better than a stick or a rock. So this is really like the beginning of science in a way of like manipulating and using matter. Okay. Later, they actually figured out how to make ores and melt them together in something called an alloy. We use alloys all the time. Basically, an alloy is where you take two different metals, you melt them down, mix them together, and then let them cool. So like we were literally talking liquid metal, mold them into like the shape you want, and then let it cool back down. And now sometimes you have a very, very strong sort of thing. I've actually got a list on the next side here. One alloy they discovered was bronze, which is copper and tin. Another alloy was iron and carbon, making one of the most influential metals combinations we have now, steel. We use steel for so many things these days. Steel is super, super strong. On its own, iron's pretty good. But one of the big problems with iron, it rusts. What happens over time to things that rust? They become physically weak and they will break. Carbon, kind of cool on its own, but most carbon is actually very brittle. If you guys don't know this, the lead in your pencils isn't actually lead. It's actually graphite, which is carbon. Yeah. It's silly that we still call it lead because it's not lead, it's carbon. And so think about trying to build a bridge out of pencil lead. Would that work well? No. So you've got one thing that's really brittle, it's going to break. You got another thing that rusts. But here's the cool thing. Melt them down, put them together, you make steel. We make so many things out of steel these days, right? Like bridges and buildings, right? Steel is one of the strongest things we have. And if we make stainless steel, then it shouldn't corrode, and it should last for a really long time. So, here's one of the other cool things is then this is now the age where we started talking about things like armor and swords. I'm thinking of like King Arthur and like, the Knights of the Round Table, right? Science has usually been at the forefront of major revolutions in history because the person or the country who has the better technology usually wins the fight. Think about this for a second. If one side is fighting with bows and arrows and the other side is fighting with a sword, the sword usually wins, right? But then if one side is fighting with a sword and the other side is fighting with a gun, well, then the gun wins, right? And now in modern day technology, if one side was fighting with a tank and then the other side developed the atomic bomb, well, that's how World War II ended, right? The Germans, if you guys don't know this, the Germans were fighting with tanks, which for a while, tanks were way better than men fighting with guns in trenches. But when the Americans in the Manhattan Project developed the atomic bombs, you guys heard this before? Right? Where did they drop the atomic bombs? Over Japan, yeah. And that was actually more or less the end of World War II because they just dropped 2 nuclear warheads. Unfortunately, it devastated Japan. But Japan and Germany, they basically gave up after that because how can you compete with that? Anyways, the point I want to make is that science is usually at the forefront of major revolutions in terms of wars and stuff. And we can see that through like the knives and armors, things like that. Okay, now fast forward a little bit. We're now not talking about people who are just literally making tools, but we're talking about philosophers who are trying to figure out, like, well, what is this table made of? What is this paper made of? What is it made of? And I have a little note here. Remember, they didn't have microscopes. They couldn't zoom in and look in really close at what stuff was. And so it seems crazy at the time, or it seems crazy now, but at the time, Aristotle, he thought he had it all figured out. He thought that everything in the world was made up of four things: fire, air, water, and earth. And they had some crazy theories. They didn't know about gravity yet. So when something falls, they literally thought it was because dirt likes to be lower than leaves, and that rocks like to be lower than dirt. Like, they thought that was the rationale. We now know that, well, rocks were just there first, and then dirt fell on top of it. But like, they actually thought that like there was like an order to things. Like, they didn't know what stuff was at the time. Another famous philosopher, Democritus, he actually had a pretty good idea though, and we actually use his idea to this day. He thought that all matter was made up of tiny particles that could not be divided. I'm going to give you an analogy here. Imagine that we had a pizza. Imagine that we had 10 pizzas, because there's a lot of people. Okay? And everybody I gave a slice of pizza to. Okay? So there's enough pizza for everybody here. But let's say more kids came. And so I needed to cut your slice of pizza in half, so everybody got some more. And then some more kids came, and I had to cut that in half again. And so now you're getting like a sliver this big, because we got to share with everybody. And then more kids come, and more kids come. Well, this was Democritus' idea as well. What if we cut something in half, and in half again, and in half again? Is there eventually a limit where I can't cut it in half anymore? Like, is there like a fundamental thing where I literally cannot cut it in half anymore? It's as small as it can get. That was his idea. And he actually gave a name to it. He called it atomos, which in, I believe, ancient Greek meant indivisible. We actually still use that word today. Atomos is the root of the word atom. Yeah. And so we actually credit Democritus with the idea of an atom, literally the smallest particle we know of. Okay, well, fast forward a little while later, we're now talking more like the Middle Ages, the medieval times, if you know much about that. Sorcery and witchcraft might have been a little bit more common. And there were a group of people called alchemists, who we wouldn't necessarily call them chemists, but they were kind of like chemists mixed with magicians. That's kind of what they did. And they were trying to do something really interesting. They were trying to turn lead into gold. That was their goal. They wanted to try to basically turn everything into gold. You guys ever heard of like the story of King Midas and his hand of like golden touch, when eventually he like turns into gold himself or something like that, however the story ends? At this time, everyone was obsessed with gold, and so the alchemists, their goal was to try to change lead into gold. We now know that that's actually not possible. You can't change one element into another, but that was their goal. But one of the cool things is that they led to a couple of useful discoveries. One is that alchemists, in their attempt to try to turn lead into gold, the word you might hear is transmutate, by the way. Maybe we should write that down. When they wanted to turn things into gold, they were trying to do something called transmutate, or transmutation. Now, they weren't successful. You can't actually turn lead into gold. Because honestly, like, if we could do that, wouldn't everybody just be doing that right now? So, that's not actually possible, but I have two things that they did that were useful. They discovered hydrochloric acid, which is quite useful stuff, and they also started the trend of having sterile, cleaner environments for labs, and they actually started using glass for putting chemicals in. We actually still do that to this day. All of the beakers that I showed you guys are basically like more or less glass. They're not actually glass. They're actually Pyrex, but good enough. It's called glass. Do you guys know what they used to put their chemicals in before they developed glassware? What was that? Not wood, actually. Not metal. Clay. Yeah, they used to use clay pots. One of the downsides to using something like that, though, is that if they used clay or pewter or something along those lines, is slowly over time it's going to dissolve and it's going to contaminate your chemicals, right? And so although you might have like a clay pot for putting water in, if you left the water in there for like 6 months, it's not really going to be clean water. Question? Are you stretching? You know what I'm saying here? And so the alchemists, although they failed horribly in their magician-y kind of ideas of turning lead into gold, they actually really contributed to science because it's the first recorded knowledge of trying to like keep your chemicals uncontaminated. Because glass doesn't contaminate your chemicals over time. I can leave water in a plastic water bottle for years, and it should be perfectly fine. But I wouldn't drink water out of a clay pot after it's been sitting there for 2 years. You know what I mean? Like it's gonna leach into it over time. Drink everything out of a clay pot? That'd be cool. Just don't drop it. Okay, now I want to fast forward to, I want to think it's like around the year 1600, 1700, sometime around then. And this is really one of the first scientists who had a huge contribution. His name was Anton Lavoisier. I don't need you to be able to pronounce it right, but he was French, so you got to put kind of the French sounding to it. So it's Anton Lavoisier. And he made one of the most important discoveries maybe of all time. He was messing around with some chemical equations, and he was weighing them on the scale. And he discovered that if he started with 5 grams of stuff that he began with, when he was done, it always ended up at 5 grams. If he started with 8 grams, he did a chemical reaction, still weighed 8. And so he came up with this law that we actually now know to be true through countless years of testing. Maybe you've heard it before. It's called the law of conservation of mass, which basically says that there's a finite amount of matter in the universe. And you can't lose mass or gain mass out of something. It always has to start at a certain weight, and however much you start with, it always finishes at the same weight. And that was a really important discovery because before that point there, I want to use an example of burning wood. Imagine that you burn some firewood. Okay? You weigh this log of firewood, it weighs 10 grams. Okay? Then you burn it. Well, it turns into ash, right? Let's say you weigh the ashes, and it only weighs 5 grams. You might think that something was lost. Well, Lavoisier realized that there was also gas being given off. Do you guys know what gas is also given off when you burn stuff? It's a huge issue nowadays for climate stuff. Carbon dioxide, yeah. Lavoisier realized that even though it seemed like it started at 10 and finished at 5, what he had missed is that gas was bubbling off. And the gas was like the missing weight. We now know that putting carbon dioxide into the atmosphere is actually quite bad for our environment. But anyways, he was the one who realized that mass always should equal each other. I have a few more things that he did as well. He actually made another important contribution. He developed the system of naming chemicals. And we're going to learn about how to do this next week, about how to name things like sodium chloride, calcium carbide, barium oxalate, right? He actually was the one who realized that we should start having a common name for stuff. Because if I call this thing over here sodium chloride and you call it blah, 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 well, that doesn't work, right? Like we all need to use the same system. And one of the cool things is we still do to this day. The naming system that we use is the same in Canada as it is in the United States, as in England, as in Russia, as in Thailand, even in other languages. We still have a consistent periodic table. And Lavoisier was the one who kind of started that. So he was actually known as the father of modern chemistry because he came up with the idea of let's all use the same words. Right? It wouldn't be fair for me to call this a table and for you to call it an apple because that's going to confuse people, right? Well, the same principle applies to chemistry. We should call the same thing everywhere. So when I talk about water, we all know what water is because we're all using the same word for it. You know what I'm saying? I know it sounds so silly, but before Lavoisier, no one had a common name for calling stuff. And I might call this something, you do call it something else, and no one knew what they were talking about. So, okay, now the next person we're going to talk about, John Dalton, built on models of matter. He was curious again about, well, what is stuff made of? And he put forward 4 ideas that he thought stuff was made of. And I have them written down here. I'll read them one at a time. He didn't necessarily have original ideas because he kind of stole this one from Democritus. But here was his 4 points, and he wrote this in a paper, and he published it and said, this is what I think stuff is made of. Only he wouldn't have used the word stuff, he would have used the word matter. So here's the 4 points. And if I could give a suggestion, put a star next to this or highlight this. This would be something that would be very, very likely testable. Okay? I'm giving you a hint here. Like this is going to be on your test eventually. So here's his 4 points. Point 1. He thought that all matter was made of small, indivisible particles called atoms. That wasn't a new thought. He basically stole Democritus' idea. But he basically thought that there's a smallest, you can't cut it in half. There's got to be something that's as small as you get. He's kind of right. We call them atoms. We use a periodic table for them nowadays. But he didn't know about things like protons or neutrons and electrons, if you've heard of that stuff yet. So he was kind of right on that, but not all the way. He had another idea. This one was pretty influential. He thought that all elements were the same as each other. If there was a copper here, it had to be the same as a copper over there. They weren't different. If we're going to call you copper, and we're going to call you copper, you have to be the same. Okay? So it's not fair for me to have a copper that's blue, but then also have a copper that's yellow. Does that make sense? That was his theory. So all elements have to be this exact same in terms of their properties. Right? And that actually is kind of true. We even saw that today in our lab. If I were to ask you guys the properties of, what did we use, magnesium? If I gave you magnesium today, and then I gave you some magnesium tomorrow, a different batch of magnesium, should they not react the exact same way? Shouldn't magnesium be magnesium, whether it's this one here or this one here? So that was his idea. Another one right here is he figured that different elements then have different properties. So if you're the same element, you should have the same properties. He figured if it's different, it should be different. So copper should not react the same way as magnesium. And magnesium should not react the same way as oxygen. Everything should be unique. That's a good idea. And then here's the important one. The last one he realized is that atoms of elements should be able to combine to form new substances. And the word we now give to these is we call these compounds. He really determined that if you combine, say, hydrogen with oxygen and maybe put them in fixed ratios. This fixed ratio means for every 2 hydrogens, you need 1 oxygen. This makes a compound. And I'm pretty sure you guys know a few compounds offhand. Like, you know this one here, right? This is water. Does anybody know what this one right here is? Carbon dioxide, yeah. He realized that things form together in specific ratios. This, by the way, in case you don't know how to read this, means this 2 means you have 2 hydrogens. And this oxygen means you just have 1 of them, because there's no number next to it. Carbon dioxide then has 1 carbon and 2 oxygens. Here's another one maybe you've heard of, CH4. Anybody know what this is? It's okay, I wouldn't expect it. It's methane. Methane involves 1 carbon and 4 hydrogens. So anyways, that was Dalton's idea, is that elements don't have to just be copper or just be hydrogen or just be oxygen, but they can combine and form compounds. And then compounds can combine and form mixtures. So anyways, these were his 4 points. Write these down, star them. It's something that I will test you on. I'm just giving you a hint at the front. Okay, I gotta keep an eye on time. The next scientist I want you to know about is Dmitry Mendeleev. I believe he was Russian. Dmitry Mendeleev. And his contribution is pretty cool. He realized that all of these elements that people were learning about, copper and boron and carbon and oxygen, he realized that just like Dalton thought, they all had unique properties. And so what he did is he started writing down some of their properties on cards. And so he started combining them together. He realized that sodium reacted with water. And so did potassium, and so did rubidium. And he started grouping them together. He started putting them in lines where, well, this one's kind of like this one, like this one, like this one. I kind of, when I see this in my mind, I think of how my daughter, Kinsey, she's 5. She likes to group things together sometimes just based on silly properties. Like, she'll put 2 completely different things together, and I'll be like, why did they go together? She'll like, well, they're both red. Fair enough. You know, I mean, to a 5-year-old, that makes sense, right? Or, you know, why did you put these 2 things together? Well, they both start with the S. You know what I mean? Well, in that same sort of way, that's what Mendeleev did. He realized that just like we did in our lab, these things burned. So he put them together. And these things over here, they reacted with water. He put them together. And these ones over here, they're all shiny. He put them together. That makes sense? And then he started grouping them in rows up and down, and also in columns side by side. And he started making a periodic table as we know it, and it started looking like this. This is one of the coolest things. This is my favorite part of the story. Mendeleev, though, he realized that if his pattern made sense, that he had to leave some holes in the table. So he actually left some gaps. can we wait to flex? Is that okay? Okay, find me a flex. Thanks. He actually left some gaps in the table, and he made a prediction. I mean, a bold prediction. He said, I think that one day we will discover new elements. Which, I mean, that's bold to do, because people thought that what they saw, carbon, copper, oxygen, they thought that's all there was. He made a prediction. He went out on a limb and said, one day, maybe not me, but one day someone is going to find this element. You know the cool thing? In all cases, he was right. And they actually eventually found scandium and gallium and germanium and technetium. And when he made his periodic table, no one had ever seen these things before. But 50 years later, 100 years later, someone was able to fill in the hole on the periodic table and say, this one goes here. Isn't that cool? Like, that literally is the definition of science. It's making observations, but not just making an observation, making a prediction and saying, I think this will happen. And he was right. So that's so cool. Okay, I'm going to do one more. No, I got a few more minutes here. We can make it. The next scientist I want to talk about is a guy named J.J. Thomson. And he used a really unique contraption. I've got a picture here of it. This is called a cathode ray tube. And sometimes we abbreviate it CRT. I'll spell it for you, though. It's called a cathode ray tube. Not quite, actually. It's, you know how old TVs used to be like the big box? Not like the modern plasma, the flat screens, but like the old big cube TVs? They actually used cathode rays in them to actually make the picture on those TV screens, but we don't use them anymore because they're so big and bulky. But it's kind of like a light bulb, though. Okay. He did not know what cathode rays were. He was shooting these particles towards a screen, kind of like how a TV was actually shooting particles towards the TV screen to make a picture, but he didn't know what they were. The cool thing was, though, is he could deflect them using magnets, and he could deflect them using different charged plates. And so what would happen is these cathode rays would shoot through this tube, and then he'd put a magnet here, and he could make it so these particles could all of a sudden either go up, go straight, or go down, depending on how he manipulated stuff. He had no idea what he was using, but he had this theory. He knew that they were smaller than the smallest atom. Now, the smallest atom that people knew of at the time was hydrogen. Okay? And I'm going to give you guys a periodic table tomorrow or the next day, but you guys have heard of hydrogen before, right? Okay. Hydrogen is as small of an atom as we know. He was able to weigh these things and determine their mass, and he realized that they were 1,000 times smaller than hydrogen, which blew a giant hole in John Dalton's idea here that all matter is made up of small indivisible particles called atoms. Because at the time, people thought that hydrogen was the smallest thing there was. But he was playing around with these cathode rays, and they were clearly smaller. And he didn't know what they were. Well, later, he realized that they were actually electrons. You guys ever heard of electrons? Okay. Sometimes I just need to check and make sure that I'm not using vocabulary you haven't heard. But we now know that electrons are actually part of an atom. There's actually things smaller than atoms themselves. There's protons, neutrons, and electrons. And he was actually shooting a stream of electrons. Nowadays, when we shoot streams of electrons at things, that's usually electricity, right? When electrons are going in a row and going in a loop, that's electricity. He just didn't know it at the time. So he had this theory then, and this is where I'm going to finish because we got to go in a minute here. He had this theory then that all atoms were not indivisible. At the time, people thought that every atom was like a ball, where it's like this one's a copper, and this one's an oxygen, and this one's a hydrogen, and this one's a neon, and that you cannot break it apart. You know how I took the tin and I kind of snapped it in half? The theory at the time was that you could not snap a neon in half. It's as small as it gets. You could not cut a copper in half. But based on his evidence, he had this new theory, and he thought that maybe there were positive and negative charges inside of atoms. And he was kind of right, because there are positive and negative charges. Do you guys know which one the electrons are? Okay, electrons are negative charges, and protons are positive charges. If you haven't heard that before, let's write that down. Negative, well, it's actually here. Negative are electrons, and so he had a theory that an atom, there's actually stuff inside. He figured that there must be little dots inside that were these negative electrons. And then he figured that the rest of it must be positive. So he figured that like the rest of this like area in here must somehow be positively charged. That was his theory. And because It was brand new. He gave an analogy. He compared it to something called plum pudding, which we don't really use anymore because it was like a 1700s dessert. But basically, think of like a muffin. Okay, the muffin dough he thought was positive, and then the chocolate chips inside he thought they were electrons. And he thought that you could actually cut the muffin in half, look inside of it, and go, "Hey, cool! There's something inside there." I know that sounds so silly nowadays because maybe you've heard these ideas, but at the time that was revolutionary. No one realized that you could actually slice an atom into pieces and realize, hey, look, there's protons, neutrons, and electrons in there. So, long story short, his theory then was that rather than it being just like one thing, all solid, never cutting up, the new theory is that there's actually these little bits inside, like raisins or like chocolate chips, and that these raisins here are negative. That was his theory. And he was kind of right, but he wasn't all the way there yet. So tomorrow we'll have to finish off the lesson, and we'll talk about a few more scientists and the contributions they made, and we'll kind of finish up there. Does that work for right now? So I'll pause this for now. One last parting thought before you go. Don't forget, sometime before the end of the day, finish up, if you haven't, or mark your safety assignment, okay? Keys on the board. When you're done marking it, throw it in the bin. I strongly recommend, guys, you should do this, because there's two advantages. One, I don't have to mark it, and I like that. No, that's actually not the advantage. One, I really want you guys to be able to get feedback right away. If you're making mistakes, I don't want it to be like a month before you know about it. Okay? And two, I really think this helps build some important skills for taking care of things, just like me and getting audited. I want you guys to be able to organize, keep track of stuff. Okay? If you do this, you can omit this assignment if you do poorly on it. Okay? If I have to mark it, it has to count. Okay, we'll see you guys later. Okay, so last day I didn't get a chance to finish off these notes. I'd like to do that real quick here, and then we should be able to give you guys some work time to finish a few tasks. So I just want to change that attendance real quick, though. Okay, so last day we were talking about a whole bunch of scientists in history that are worth knowing, mostly to their contributions of matter. Do you guys remember what the definition of matter was from yesterday? Anyone recall it? Nice. Yeah, I heard a couple of you guys get it there. Has mass, takes up space. Those are the two requirements. Fire doesn't count. Outer space doesn't count. Those really aren't matter. But everything else, that would be considered matter. And scientists for, well, I mean, up until about the last century, scientists for millennium have been trying to figure out what stuff is made of. Now, we're getting to the point now where there was a huge advance in technology. And I don't actually have it written down on my slides, but does anyone want to guess what the big advance in technology was that allowed us to understand the structure of matter a little bit better? Not telescopes, but super close. Microscopes, yeah. What's the difference between a telescope and a microscope? Well, yeah, go ahead, take it, Sam.
Telescopes are like far away things that are big, and
Yep.
microscopes are like really close things that are big.
Exactly, yeah. Micro meaning small. Micro is the like Latin prefix of small. We would want to use that for things that are super, super tiny that you want to zoom in on. Whereas a telescope is actually trying to make something that's so far away be visible because it's too far for you to actually see. So telescopes are used for outer space, like to see asteroids and moons on different planets. But microscopes, now that was a big one because once microscopes were developed, scientists were actually able to start looking at the internal structure of matter. And some of those things are pretty cool. Now, we're actually not to that point yet, though, in where I finished off our notes. So I do want to just finish up this slide here. Just wondering whether I should close those doors or not there. Yeah, I'm going to do that real quick. Give me a sec. Lav has a booming voice. All right. Okay, so yesterday we were talking about a lot of scientists who are trying to contribute to our understanding of what stuff is made of. And we got up to a part right here with a guy named J.J. Thomson, and I just want to do him one more time here just to make sure I didn't miss anything important. So J.J. Thomson at the time, he lived at a time where scientists believed that all of the stuff, all of the matter, was on the periodic table, which actually is kind of true, right? They knew about things like hydrogens and sodiums, and they kind of had this thought that all hydrogens were kind of the same as each other, and all coppers were the same as each other. But they also had a thought that you could not divide an atom into pieces. They figured, like, if you had this atom like a ball, you could not cut it in half. That was the theory. It was actually based, really, the guy who had this theory, John Dalton, it wasn't really his idea. It was actually Democritus' idea from thousands of years before, and it was based on the Greek word atomos. And the Greek word atomos literally means indivisible. And so they figured that what's on the periodic table is as small as it gets. You cannot cut it in half. And then came J.J. Thomson, and he began working with something called a cathode ray. Now, he didn't know it at the time, but a cathode ray was actually an electron. And one of the cool things about it is that these cathode rays, they took up space, and they had mass, but they weighed such a small fraction of the smallest previously known thing out there. Previously, the smallest element that scientists knew of was hydrogen. And so hydrogen weighed, say, this much. Well, these cathode rays, it wasn't like they were a little bit smaller, or a little bit smaller here. They were over 1,000 times smaller than hydrogen itself was. And so, like, you've got your copper, which weighs a lot. You've got your iron, which is a little bit lower. Your neon, it's a little bit lower. The lightest thing in the world is hydrogen. And then comes Thomson playing with these cathode rays, and they are 1,000 times smaller than anything before. And it just blows a giant hole in this theory of atoms, which kind of stinks. Because up till that point there, they thought that they were actually pretty smart. It's like, yeah, we got this science thing figured out. And then, well, how do we explain this? So I want to show you this contraption he used. This is known as a cathode ray tube. Did I write that down yesterday? I think I did. I'll write it down one more time just in case you want to have it written here. It's called a cathode ray tube. And until recently, we actually used them in our televisions a lot. Like the big box TVs use them. Here's how it worked. He shot electricity. And you know what? Electricity are actually, we know this is now electrons, but he didn't know it at the time. He shot electricity, basically electrons, through this vacuum tube. And right about here, he had some magnets. And the magnets caused these particles to deflect. And that was really interesting because what it meant is that they were charged. I don't know that I used that word at all yesterday, but he discovered that they were charged. Does anybody know what charge an electron has? Negative. Electrons are negatively charged. Does anybody know the opposite of the electron's charge? It's a proton, yeah. Now, at the time, scientists didn't know about this. We now, maybe you've heard these words, electrons, protons, and neutrons. And those are actually things that are smaller than atoms themselves. They're what actually make up atoms. And this was the first evidence the scientists had that hydrogen and helium and all the periodic table elements weren't actually as small as it gets, but you can actually zoom in even more and even more. To this day, scientists are actually trying to figure out what stuff is made up at a smaller level. Any of you guys watch Big Bang Theory? Ever seen that TV show? Okay. If you've seen the show and you know the guy on the show, Sheldon, if you've heard of him, he in the show is a string theorist. And modern day physicists have a theory that if you keep getting smaller and smaller and smaller and smaller, smaller than an atom, smaller than an electron, smaller than a quark, which is even smaller than that, they believe that maybe at like the even more fundamental level, all matter is made up of strings. You know? And it's really hard to prove, and it's mostly theoretical, but like if you ever heard them mention that on the show, string theory, that's kind of the same concept as this, only like 300 years in the future. Right? Atoms, then what's smaller than an atom? Well, what's smaller than that? Well, what's smaller than that? And so that's kind of like, it's actually progressed continually. Anyways, I'm getting off topic. Thomson then had this idea. He suggested that rather than an atom basically just being like a solid sphere, and if you wanted to try to cut it in half, you couldn't. That was the previous theory. He suggested maybe there's something inside. And so he used a common dessert at the time, which we don't really eat at all. It was called plum pudding. I like to think of a muffin. Okay? So basically the idea is if you had like a muffin, I'll just draw a circle. I know a muffin's not a circle, but imagine a muffin. and you had chocolate chips all baked inside of it. Well, his theory was that maybe these cathode rays, which we now know are electrons, maybe there are electrons inside of the atom. But here's the thing, if electrons are negative, we have to have the opposite. You have to have, the positive and the negative, the yin and the yang. So he realized you couldn't just have negatives. You'd have to have some positives somewhere else. So he thought, well, what if the remaining stuff was all positively charged? So he had an idea that like all of this area in here, this would all be positive charged, and there'd be all these little negative dots inside. And he figured that these negative dots, he figured those were those little cathode particles, those cathode ray tube particles. Does that make sense? That was his theory. And he wasn't right by any means, because that's not how we think matter works to this day. But it was important to note because of the change of, they used to think that this was as small as you could get, and he thought maybe there's something smaller. Okay, the next scientist I want to talk about, actually his work was done just over 100 years ago. And he was Canadian, which is a really cool thing. Ernest Rutherford actually worked at McGill University in, I believe it's in Quebec, which is kind of cool. So there's actually a Canadian connection. And he had a really cool experiment where what he did is he fired some particles at high speeds at gold foil. And I just want to show you the picture on the next slide. So if you have your notes in front of you, maybe it's below it, isn't it? Okay, don't even change the page then. This was the idea. He emitted some particles, some really, really, really small particles out of like a radioactive box, and he shot them at some gold foil. Now, just for the sake of argument here, I'm going to replicate his experiment, only rather than using particles, I'm going to use a marker and the whiteboard. So here, I'm going to throw something at it. What's happening? Every single time it hits the wall and falls. Right?
Yeah.
Well, this is our reality. We live in a macroscopic world, a big picture world. But he was testing things on a microscopic scale, something really small. And he had very, very, very strange things happen. You would expect all these particles to hit the gold and then just like fall down or something like that. And instead what happened is they all phased through. So imagine I throw all those pens at the wall and they end up on the other side of the wall. Wouldn't that be strange? And obviously Harry Potter's magic, right? But that was very, very confusing at the time. Because it was like, how is that supposed to happen? How am I supposed to put these particles and have them phase through? But here's the even more strange thing. Most of them phased right through the wall. So it's like they're mutant particles. Except a couple of random ones, just a few here and there, actually did what you expected and actually bounced kind of backwards. This made no sense. You would have figured that they all would bounce backwards. And yet, they all phased through. I think he could have accepted the fact that they all went through and been like, okay. But the hard part was like, why did a few of them bounce backwards? So he had an idea. He thought that maybe what was actually... Oh, let me show one more picture here, actually, before I get to what his theory was. Flip the page over, would you? This is another kind of picture of what happened. He shot all of his particles, and they all went through. How do they phase through matter? How can you physically go through something that's solid? And then the weirder thing here is this is what he expected then, but then a few of them bounced back even. So here's his theory. Where is a good picture here? I don't have a good picture. Okay, here's his theory. It's on this page here. Sorry, I bounce around a lot. He thought that maybe rather than having a model where you have these little dots all inside, he thought that maybe there was something called a nucleus. Here we go. A nucleus. Where all of the heaviest matter part of it was all concentrated right in the center. Right here, right in the middle. And that the electrons, rather than the electrons being kind of inside, you know how like the pudding model was that the raisins were inside? He figured, what if the electrons were actually on the outer rim? And he was inspired by our solar system and by planets. Because his idea was kind of like how this is the sun. And the sun is really dense, really heavy right in the middle. And then the planets... You know how the planets kind of orbit the sun, right? That was his inspiration. He figured, what if everything was all compacted in the middle and the electrons were just kind of on the outside? His model would have looked something like this. I'm just going to draw a picture here. Rather than having like a whole bunch of billiard balls in a row, which would have been the previous model, if I were to shoot something at it, you wouldn't expect it to go through, right? But here is his theory. Let me just draw another one here. He figured, what if there was a nucleus and there were a whole bunch of particles all packed together here and here and here like this. And then there were electrons that were kind of orbiting not on the inside but on the outside. And the electrons still took up space, but they took up space and it looked more like this. This was his theory. Okay. Now say you want to shoot some particles at it. Well, now I shoot a particle through. It doesn't have anything to hit because all of the really dense, heavy particles were all stuck in the middle. And I throw something through right here. All of the heavy, dense particles, it misses. But here's what explained the weird thing. Remember how a few of them actually did hit the wall and bounce back? What if a random one actually did manage to hit the nucleus? Well, then it would be just like I threw it at the wall, and it actually would bounce back. And so he had a new idea. Think of it as like flipping the model around. Rather than having the ball with the electrons inside, he figured, what if there was a really, really small one and the electrons were outside? The electrons wouldn't cause the matter to bounce. Remember how small electrons were? They were 1,000 times smaller than anything else we'd have ever seen. So any electrons that might be out here, like here's an electron, here's an electron, it's so small that if something manages to hit the electron, it's not going to stop it. Okay? But if it does hit right here, it bounces back. So this is a really cool idea, and it introduced the idea of, right here, the nucleus. So a nucleus basically is all the material is now in the middle, and the electrons are floating around it. And just like with a lot of scientists on this list, he wasn't totally correct because actually electrons don't go around in an orbit, we've discovered. But he seems to be right about the nucleus concept. And so that's why we talk about him, is that he introduced the idea of the nucleus being here. However, it was like not even 2 years after he made his discovery that he himself knew his model was wrong. And one of the reasons why it has to do with electromagnetic radiation. And I don't know that I can explain the whole thing to you guys because we have to build our way there. But the long and short of it is that if things actually were orbiting in circles, two things would happen according to some other laws. They would actually not go around in like perfect circles, but they would eventually spiral in and like crash into the nucleus. The Earth doesn't go around the sun like that. Think about how horrible this would be. Here's the sun, and the Earth goes around the sun. What would happen if the Earth were to slowly but surely get closer and closer and closer and then crash into the sun? That'd be horrible, right? Yeah. But the good news is that's not how Earth works. Earth just keeps going in its perfect orbit around and around and around, never getting closer, because otherwise we'd burn up, never getting further away, otherwise we'd get too cold. However, electrons behave differently than planets. Electrons should spiral into the middle, which makes no sense then because then the model would fall apart. The other reason why that wouldn't work is that there's also a theory that electrons that go in circles give off radiation, which means that all matter would be like giving us like X-rays and gamma rays and causing cancer. And we know that's obviously not true because otherwise like we'd all be dead already. So he knew within a couple of years his theory was broken because he knew that they didn't actually go around in circles, but the whole nucleus idea, the idea of taking the electrons out of the middle, like the pudding, putting them on the outside, that was new. So, wait, well, the next guy was actually like a friend and a contemporary, like they worked together. Niels Bohr, he had an idea, and this one was very, very strange. And to this day, scientists are still trying to figure out how this works. Niels Bohr suggested that unlike the orbiting idea, so I'm just going to draw a nucleus. Let's just say this is like a densely packed nucleus. He suggested rather than these things orbiting around in perfect circles, where like they literally travel in a circle, like a planet does around a sun, he suggested they still kind of go in circular paths, but they can only be found in certain spots. And he called them energy levels. He kind of said the first ring would be energy level number 1. Like this is ring number 1. This would be ring number 2. This would be ring number 3. And he suggested that they don't actually go in circles, but they are found in like rings, so to speak. But he suggested they actually can move from one ring to the next. An electron that's right here, he suggested it could go from this ring to that ring. But here's the cool thing. He suggested, and I kid you not, that it actually like teleported there. That like it physically goes from this space right here, and it instantly shows up right here. And that you would never find it like going like you never find it right here. So it's his theory that it literally jumps from here to there instantly. And all of a sudden it moves energy levels. And this is like science fiction-y kind of stuff. Because honestly, he was suggesting that electrons teleport. And I kid you not, this is what I teach my physics kids in Physics 20 and 30. We actually talk about the idea about how teleportation is actually probably possible. Because it seems that electrons actually move like this. They don't go in circles. Because we already know there's some problems with circles. But they are either found here, like somewhere on this rim, and then all of a sudden, they just jump to the other one. They don't move like you or I would, right? Like if I had to go from here to the door, I would actually have to walk to the door, right? And you could pause for a second, and I'd be halfway there. Does everybody understand what I'm saying here? Bohr's interpretation was that literally the electron instantly went from this ring to that ring, and you would never find it in between. It doesn't actually have to go there. It's actually really cool stuff. If you guys want to take more physics, it's super cool. And he actually had proof of this. And it's a very, very strange proof. I'll try to show it to you one day. But it's actually based on this picture right here. What he did is he took like a neon light. You guys know how like there's like, you know, different neon lights you might see for like a storefront kind of thing. In order to make those things light up, you basically take gas and you run electricity through them. That's how you make like a neon light in a store. He did this for a whole bunch of different elements. He shot electricity through a gas, and then he looked at it through a really special little screen. And I've got a few devices. I'll show you one later if you care. And he ended up seeing this pattern right here, which was really strange. He had one little bit of red light, and then a couple other little patterns right here. And what he hypothesized is that these were the energy levels. This was the electron in the first energy level. And then this is the electron in the second energy level. And this is the electron in the third energy level. And the reason why there was darkness between them right here is because the electron was never going to be found in between. And that literally, it had to be found here, or it had to be found here, but it was never in between. That was his evidence for it. So with you guys kind of just starting and learning more about chemistry, if you want to know more about this, I'll totally tell you more, because this is super cool stuff. But his idea radically transformed not only chemistry, but like science fiction and some of that stuff that gets written about it, because teleportation actually happens at a subatomic level. And scientists are actually working on this. I showed my class a video about how there's a group of scientists working off the coast of, I think it was Madagascar by Africa, and they were actually trying to teleport particles from one place to another. It was really cool. I don't think it's going to actually be finalized in our lifetime, but anyways, I digress. It's cool stuff. So this is another picture of that concept. Okay, electrons do exist, they figure in these orbitals, but keep in mind, Bohr's theory is not that they were actually going in circles, that they're just found wherever, right? So like it could be here, it could be here, it could be here, and literally, if it wants to go to the next ring, it can, but it just jumps. That's kind of cool. Okay. Well, Bohr's model is what we more or less work with today, but sometimes we work with like a modified version of it. We call it a quantum model. Anyone ever heard the word quantum before? It gets used a lot in like sci-fi type stuff, quantum model. And it's not really based on exact knowledge. It's actually based on a really key word of probability. If you want to maybe underline that one. This is the really key thing here. How do I describe this? Electrons are so small. We already talked about this. They are 1/1000th the size of the smallest thing people knew at the time. They are so small that the mere fact that light hits them actually causes them to move. Let me say that again. If light were to hit me, you know, these lights are hitting me, right? Clearly light is shining on me because you can see me, right? Do I get knocked back by light? But electrons, though, they are so small that if light hits them, it would actually cause it to like bump like curling stones. Does that make sense? And so this is what's really fascinating about electrons is that we don't actually know where they are sometimes. Because as soon as we look for them, the light that hits the electron and then bounces to our eyes for us to like look at them in microscopes, as soon as we look for them, the actual light hitting the electron causes it to move. So we can know where an electron was. We don't actually know where it is anymore. Say that again. We know where electrons were, but we don't know where they are anymore because as soon as light hits the object and bounces into our eyes, we perceive that it's right here. Does that make sense? Like, why do I know that you're standing right there? Light is bouncing off of you and into my eyes. But does the light cause you to like go flying out of the room when it hits you? You're not an electron. If you're an electron, it causes you to move. So anyways, the point I want to make here is the quantum model of the atom actually talks about probability, because we don't actually know where it is, but we know maybe about where it is. So they can say, well, I'm 90% sure this is where it's going to be, but we actually can't narrow it down because it's that small. Isn't that strange? It's like the physics and chemistry is actually super cool. So this is what we actually think things look like nowadays. Rather than doing like lined like circles, they actually draw them in like 3 dimensions as like bubbles. And these bubbles are where we think the electron probably is. With the problem being that like we don't actually know where it is. You know, it would be like if your mom or your teacher asked you, "Where's your homework?" You could say, "Well, I know where it was yesterday, but I don't know where it is today." You get what I'm saying here? Where's your electron? Well, a second ago when I looked for it, it was right there, but as soon as I looked for it, it actually disappeared on me. You know, and it may have just jumped to another energy level just randomly. That's the cool thing about it. So we think these things are kind of like bubbly balloons, and this is the quantum model. So that's kind of like a brief, although it did take me a while, a history of matter in trying to figure out like what is stuff made of, matter being the stuff, right? And so what I need for you guys to do is know the basics of like as we went along. The scientists that we talked about, most of them were not right. Like Bohr, we still don't think he's actually correct. We're pretty sure that there's more for us to learn. We know that Rutherford was not right. Or even Rutherford himself knew he wasn't right, like a year after he made his idea. But they made some pretty cool contributions. So I need for you guys basically just to know the history and know some of the definitions we talked about. Does that make sense? Cool. Okay, let me stop the video here. And then I'm going to give you guys almost 45 minutes of work time.